Okay, first reminder, your labs from last week are due on Wednesday at 8:30 a.m. on Google Classroom, so please make sure you have those done. Okay, I've had a few people come in asking questions and things like that. That's good. Make sure that you take advantage of that. You can come and see me. For today, we are going to start vector addition. The first vector addition stuff will seem familiar, right? It's one-dimensional vectors, and you did that in Science 10. That's forward and backward, north and south, okay, left and right. It's just positive versus negative, and those are all along the same line, so one dimension, okay? And then we're going to move into two-dimensional vector addition. We'll start with perpendicular vectors, so you go east and then you go north, and you have to go along the, just wait outside please. Okay, and then you have to go along the hypotenuse to get the change in position or displacement, okay? So we'll be looking at how you do those. That's where the trigonometry is going to come in, and then probably by the end of class, we'll start looking at having angled vectors that kind of point any which direction and how we do that. Okay, so we're going to start with the principles of vector addition, okay, simple vectors, how we draw and add all vectors, but apply it to the easiest ones first. Okay, all right. Okay, give me 1 sec here, guys. Okay, so with all vector addition, we represent vectors with an arrow. Okay, and we use two things about the arrow to represent the two parts of any vector quantity: magnitude and direction. Okay, so the length of the arrow represents the magnitude. So if I was adding a 2-kilometer vector and a 4-kilometer vector, my 4-kilometer vector should have an arrow that's twice as long. That sort of makes sense? Okay, so length of the arrow is going to represent the magnitude, and then we just draw the arrow pointing in whatever direction that vector has. Okay, 30 degrees east of north, or whatever it happens to be. All right, that's how we're going to represent that. So for this very simple vector right here, this would be a 2-kilometer vector, 30 degrees north of east. Why did I say it that way and not northeast?
It's not directly northeast, but it's not in the middle.
Right. There's only one vector that's truly northeast, and that would be 45 degrees north of east, which also happens to be 45 degrees east of north. Okay? That's the only vector that's truly northeast. There are 90 vectors between east and north. They would technically all be northeast, so we can't really do that. Okay, that's why we always say it's measured from this vector in this direction. So when you get a vector quantity like this one, which I said was going to be 2 kilometers at 30 degrees north of east. Okay, that means that I went 30 degrees from east. Okay, everyone follow me there? So whatever the second direction listed is, that's the one that was measured from. Okay, and then you went in the direction of the first vector. Okay, so I was facing facing east, and then I turned north 30 degrees. Now I'm facing 30 degrees north of east, and I'm going to walk or drive 2 kilometers. Okay? Now, sometimes, people just get that right away, okay, and other people kind of struggle with it a little bit, and that's fine, okay? There's all kinds of things you can do. If I'm drawing a vector, okay, this is how I do it. So let's say I get this vector here. Let's say I get 42 degrees, let's say it's 4.5 kilometers at 42 degrees south of west. Okay? What direction is it measured from? West. Okay? So what I do when I want to draw this vector is I draw a dotted line due west to act as my reference. Okay? And then I go 42 degrees south of that. So I just draw a little angle arc. Okay, and I say, all right, that's 42 degrees. This is 4.5 kilometers. This is how far south I go. This is how far west I go, and I'm done. Okay, everybody all right with that? That's how we draw our vectors if we're given them that way. Okay, so in vector addition then, okay, it's obviously not always going to be one vector. There's going to be more than one vector. So what we have to do then is draw the next vector. So if a question says you go 2 kilometers at 30 degrees north of east, and then you go 6 kilometers at 30 degrees north of east, where do you draw the second vector? So I have my first vector, 2 kilometers at 30 degrees north of east, and then I go 6 kilometers at 30 degrees north of east. Where do I draw the second line?
Attached to the 2 kilometer one?
Right, on the head of it or the tail of it?
Ahead.
The head of it, yeah. Okay, I would draw it here because I did this and then I did this. Whoop, that was supposed to be green. Come on. Okay, so that's my second vector, 6.0 kilometers. Also 30 degrees north of east. Right? It's like I'm telling a story. I did this, and then I did this. I have to reflect that when I add the vectors. Okay? What I see people do often is this, and they don't realize what they're saying when they do it. So let's say I have that 2 kilometer vector. Okay, 2 kilometers at 30 degrees north of east, and then they turn and go due north for 4 kilometers. Okay? I'm supposed to put that right here, because this one happened and then this one. So the right diagram would look like this. Okay, this one happened, then this one happened. But what I see people do is they go, okay, so then, and then they did this. What did you just do? You're like Don Quixote, who got on his horse and rode off in all directions. Okay? Or you're like the Scarecrow in The Wizard of Oz. Some people like to go this way, some people like to go this way, and some like to go both ways. Can you go both ways? Not unless you can split yourself in half and walk in 2 directions at the same time. No, you can't. But that's what this diagram is saying. Okay? It says you literally split in half, and half of you went that way, and half of you went that way. Okay? That's not what's happening here. What's really happening is you went 2 kilometers, and then you turned and went 4 kilometers. Okay? So we draw them in the order in which they happen. Okay? Most of the time with position vectors, people don't get that wrong. Okay? It's when they start to be acceleration and velocity vectors. They think for some reason they can't put them on the head of each other. Okay? Or really bad when we get to like forces. Okay? And 2 people are pushing on the same object, they always draw them as though they're coming from the same spot. Okay? But they're not. It's one and then the other. Okay? Always drawn in this way, tail to head. Okay? We always draw vectors tail to head. So we draw the first vector, and then we put the second vector, the tail of the second vector, on the head of the first. Okay? And if there's 5 vectors, you keep going. Right? Because if I'm looking at this trip here, what does this line represent?
Displacement?
Yeah, that represents your total displacement. Your total distance is 6 kilometers. You went 2, then you went 4. Okay? But your displacement is a vector quantity. It's that straight line change of position. Your initial position is here. Your final position is here. That's your displacement, your change in position. Right? Could you figure out how long that is? You would use trigonometry. I mean, did we not just kind of build a right angle triangle here? Okay, if I could figure out how long this side is and how long this side is, could I figure out the whole triangle and do Pythagorean theorem and all that fun stuff? I sure could. Okay, that's where we're heading. For right now, we're going to do them all on the same line because that's easier to learn. Okay. Okay, so as we said, okay, the direction of the arrow gives the direction of the vector, okay, and the length of the arrow, okay, is proportional to the magnitude of the vector. Okay, that's the conventions that we use when we're drawing vector diagrams. Okay, and we're going to use compass directions a lot, so make sure you know how your compass works. Okay, the top of it is north. All right, this is east, this is south, and this is west. Okay, it's the east and west people flip on there sometimes. Okay, make sure you've got it pointed in the right direction. So, when we have to add one vector to another, we draw them tail to head, as I just illustrated a minute ago. So if we have these two vectors here, right, the first vector is 275 meters due east, right, so that would be this vector here. And when we draw vectors, sometimes some books will tell you to draw it like this and use like D, A, B. Okay, put in the actual vector, 275 meters. Okay, that, if we know how long that is, we should write in how long that is. All right, and then it goes 125 meters due east. Okay, so then I draw my next vector on. And what I try and do on the board is I draw them in different colors so that they stand out a little bit better. You can totally do that on your paper as well. Okay. Okay, what's my total displacement?
meters.
400 meters
East.
east. Yeah. Okay. Is that very difficult? Okay. Collinear vectors. They're one-dimensional. They just go along that line. Right? Now, if instead that question had said that they turn and go 125 meters west, how would that diagram change?
Arrows pointing the way.
Right. This one would, the second one would point backwards. Okay, I still draw them tail to head. I did that one, and then I did the shorter one, and I came back a little ways. Right? What's my displacement now? $150 meters. Which direction? East. Yeah, I'm still east of where I started. Okay, I went 275, and then I came back 125. So now my total displacement's 150 meters east. Okay. Everybody all right with that? Is that ringing a bell from Science 10? Okay, you totally would have done ones like that in Science 10, but you probably wouldn't have drawn them. Okay, you'd have just gone, oh, I need to subtract those, or oh, I need to add those. Okay, so all vector addition is done tail to head. Right? Really important to know that that is the convention. All vector addition. Doesn't matter what vector quantities you're adding. They're drawn tail to head. Force, acceleration, velocity, position, and they're all drawn tail to head. Okay, questions so far? All right, so collinear vectors are pretty easy because they can only ever be positive or negative. Okay, but they get more complex when you start changing directions and making turns. Okay. All right, so let's say we do this. First, we go 275 meters due east. And then we turn and go north 125 meters. Okay, my distance traveled is still 400 meters. But now my change in position is less than that. Okay, so I went 275 meters east, then I turned and went 125 meters north. How do I figure out what my, or which line on there represents my displacement? The red one. Yeah. Okay, how do I calculate how long the red line is? Yeah, I use Pythagorean theorem. A squared plus B squared equals C squared, right? I mean, it's a right angle triangle. It should be able to do that. Okay? Now, I'm saying that that line represents the displacement, is displacement of vector quantity. All right, so I can't just do Pythagoras and go, I'm done. That only gives me a magnitude. Okay? This also has a vector. If I know these two sides, can I figure out what theta is? All right, here's your Math 10 stuff. SOHCAHTOA. Okay, being able to do trigonometric ratios. Well, really trouble with that one. Okay, trigonometric ratios. All right, since on that one I would have the opposite side and the adjacent side, which trig function would I use? Okay, I see people shaking their head going, I don't know. Okay. Hypotenuse never looks right. Is it UE or EU? Doesn't matter, you know what I meant. Okay. Okay, so cos, you use adjacent over hypotenuse, and tan, okay, so TOA, whoop. Okay, so tan is opposite over adjacent, sine is opposite over hypotenuse, cos is adjacent over hypotenuse. Since I know the opposite and adjacent sides, which one am I going to use? Tan. Okay. All right, let's walk through this example then. So I want to calculate the displacement. We already said the first thing I'm going to do is do Pythagorean theorem to get the magnitude of d, okay, or the displacement. So the displacement, the red line, is going to be the square root of 275 squared plus 125 squared. Okay, so we're looking at 302.08. Alright, that's the magnitude of my displacement. Now I need to get the direction. Actually, at this point, I now know all three sides of the triangle, so you could use any one of those trig functions you wanted. Okay, for me, I'm going to use the two the question gave me, just in case I messed up my calculation at some point. Okay, so I want to find out what theta is. Okay, so theta, or sorry, I'm going to use tan. So tan of theta equals opposite over adjacent. Okay, so if I want to find theta, I bring tan over here. Theta equals the inverse tan of the opposite side over the adjacent side. That will be 125 over 275. How do I tell which one's opposite and which one's adjacent?
Opposite is directly opposite of the angle.
Right. The angle doesn't touch the opposite side. The angle arc does touch the adjacent side. Okay? All right, so if I do that calculation here, okay, we are going to have second tan of 125 divided by 275. All right, so that's going to be 24.4 degrees. Can I leave it like that? What else do I need to put on there? North of east. Nicely done. Okay, how do I know that this is north of east and not east of north? Well, because it's touching east. That means I went 24.4 degrees north of east. You got to look at that arc. Whatever side that arc is touching, that's the direction that goes second. It's the one that was measured from. Okay, so in the end, we would have three significant digits on this. So our overall displacement would be 302 meters. Actually, sorry, we only have two significant digits, because that 30 only had two, didn't it? Nope, everything has three. Okay, 302 meters at 24.4 degrees north of east. Okay, questions on what we did there? Okay, is that exactly the kind of thing you would have had to do in Math 10? I know, my son was in Math 10 last semester. I know, because I had to work with him on it. I know it's exactly what you did, okay, in Math 10. Okay. All right. So this is just showing again, okay, what we did there. Okay. All right, so we're going to look over a couple of examples here, just try those together. All right, give this one a try. These people live in the most boring village in the entire world. Okay, and they're in a snowshoe race where they move forwards 10 meters and untie a series of knots. And then they move forward 5 meters and solve a puzzle. And then they move 25 meters forward to the finish line, because reasons. Yep, it's all forward. Okay, so show your calculation of their overall displacement. I actually want the vector diagram drawn here, which is going to be super easy. I'll give you like 15 seconds. All right, if I'm drawing a vector diagram of this situation, okay, I would go like this. 10 meters. 5 meters. 25 meters. All right, what's my total displacement? Meters forward. Okay, everybody all right with that? They really don't get much easier than that. Okay. I'd like you guys to try number 7. Kind of vectors, kind of also an algebra trick. Okay. Start by drawing the diagram as much as you can of the diagram. Okay. And then you can set it up algebraically and see if you can get it. Okay. Require a little bit of thinking. Okay. So there's 2 parts to this question. There's the vector part that helps you get something you need to do the algebra part. Okay? Now I know I'm walking around already that a few people just went, oh, common sense, I figured it out. Okay, then that's fine. You common sense figured it out. You still did the algebra part, but you just did it in your head. Okay? Maybe sometimes without knowing it, which is really cool. I wish I was that good at math. Okay? So, what this car did is it went 500 kilometers north. And then it came back in 3 different sections, but its overall displacement when it was done was 50 kilometers north. Okay, so basically we had this vector, and then this vector, and then this vector. Okay, and they're probably not very well drawn to scale here. Maybe I'll do this. That should have been easier. Okay, so now it ends up that I end up 50 kilometers north of where I started. So this is the vector part. What's my total, if my total displacement is 50 kilometers, what do the three segments add up to? 450. Okay, so that's the only reason we need to do the vector part, is so that we know this part here is 450 kilometers. Now we go to the algebra part. It never tells us how long any of these are. It says there's three sequential, and each one is 50 kilometers longer than the first, which is useless because I don't know how long the first one is yet. Okay, so here's what I want to do. Set it up like a math equation. 450 equals x plus 50. So here's my first vector, x. I don't know what it is, but I know the second one is that long plus another 50. Okay? And the next one is 50 kilometers longer than this one. So that would be plus x plus 100. Right? If the second one was 50 kilometers longer than the first, the third one is 100 kilometers longer than the first. Okay? So, can I isolate x? So if I subtract the 100 over here and the 50 over here, what I end up with is 300 equals x plus x plus x. In other words, 300 equals 3x. How big is x? 100. So that means this one's 100, this one's 150, and this one's 200. Yeah? I can't remember ever asking a question like that on a quiz or a test. Okay? The only purpose of that is to illustrate sometimes you have to use your diagram to help you get to the algebra. Okay? All right, so try number 9. This one you definitely want to draw a diagram for, but someone did bring this point up, and I do see this and I forgot to mention it. When you're drawing your vectors up and down, draw them off to the side. Otherwise, it's going to get really messy because you can keep drawing over the same line over and over again. Okay? All right, I'll give you a few minutes on that one. Okay, so for this one here, okay, if we're wanting to draw the diagram, right, we're going to start here because it's dropped, okay, falls 10 meters, and then comes back up 8, then falls back down 8, okay, so we got 10, 8, 8, okay, rebounds 4, okay, so comes up 4, goes down 4, and then comes up 2. Okay, find the distance the ball travels and its displacement from the drop point. Okay, what's its displacement from the drop point if it's 2 meters above the ground now? 8 meters down. Yeah, it's 8 meters below where it started, right? Because it's now 2 meters above the ground. What's the total distance? Okay, so 26, 30, 36. Yeah? Okay. We have to add them all up, right? Distance doesn't care which direction you go, just how far. Well, that ball bounced up and down, up and down, up and down. Okay, it's going to be 36 meters. Okay, everybody okay with that? Okay. All right, I want you to draw this one and figure out the camper's displacement. Okay, so they leave their tent and go to the lake. Okay, they walk 0.8 kilometers south, then 1.2 kilometers east, and then 0.3 kilometers north. Okay, remember, tail to head, tail to head. Okay, and then I'm going to want to see the line that represents the displacement and the calculation. All right, give you a few minutes on that one. Draw the picture first. Okay, just in case anybody's stuck, let's look at what the diagram looks like. Okay, and I'll give you a few more minutes from there. Okay, so this trip starts out at their campsite, and they go 0.8 kilometers south. Then they go 1.2 kilometers east. is this at least approximately to scale? Okay, it doesn't have to be perfect. You don't have to take out a ruler and measure everything. Just make sure it's at least approximately to scale. All right, I don't want my 1.2 kilometer line to be like 3 times as long as that one. Okay? In fact, it's probably a little bit too long. I might just shorten it a tad. All right, and then they go 0.3 kilometers north. Okay, so does that represent a tail to head vector diagram of this person's trip? Okay, where do I draw a line that represents their total displacement?
The top of point E to the top of point B.
Right, from start to finish. Okay, I mean your total displacement represents your total change in position, magnitude, and direction. So that line right there would represent the total displacement of the camper. I would say your next step would be to figure out the length of that line. And you might be able to draw a right angle triangle where you would know the 2 sides. And that might help. Give you a few more minutes. Okay, so the key to any kind of vector addition is to be able to break down a trip with many parts to one line. Okay, that line is going to be angled more than likely. Okay, but if it is, I should be able to figure out its horizontal and vertical components. In this case, the horizontal component is going to be east, and the the vertical component is going to be north-south. Okay, in this case, south at the end. Right? So, how far east does this person go in total? 1.2 kilometers, right? We know that from down here. So that means then that this side of that triangle must be 1.2 kilometers. How long is this side? I went 0.8 south and then came back 0.3 north, so how far south did I end up? 0.5. Okay, so all we did here was take our only horizontal or x component and say, okay, that's our x component, and then we took our 2 vertical components and added them together. Okay, 0.8 kilometers south plus 0.3 kilometers north equals 0.5 kilometers south. So now I have the 2 sides of that triangle. Can I figure out the magnitude and direction of my displacement? I just have to do Pythagoras. Okay, that'll be 1.2 squared plus 0.5 squared. That'll give me the magnitude of my displacement. So 1.2 squared. Okay, plus 0.5 squared. That didn't do it right. Let's try it again. 1.2 squared plus, there we go, squared. All right, 1.3 kilometers. Right? So I now know this is 1.3 kilometers long, but I still need to know what direction it went in. Could I have also drawn the triangle like this? Would that have been okay too? And it is. It's totally fine. But I'll get a different direction. Is that okay? Actually, it is, because it isn't different. It's just from a different point of view. Okay, which I'll show you here in just a sec. So I'm going to calculate it this way. That makes 0.5 my opposite side and 1.2 my adjacent side. So I'm going to say theta equals inverse tan of opposite divided by adjacent. Okay, so I get that that's 22.6. I only have 2 significant digits, so it's going to be 23 degrees. Okay, and that is south of east. Okay, now if I do that triangle the other way, okay, if I do it this way, I'm looking for this angle. That makes my opposite side 1.2 and my adjacent side 0.5. Am I going to get the opposite angle? Or let's say the complementary angle to that 23 degrees. Looks like it to me. Okay, so instead of getting 23 degrees south of east, I get 67 degrees east to south, same direction from different points of view. Either one of those would be the correct answer because they're both right. Okay, and they're both the same direction. Okay, so every vector addition question is going to come down to this step. Finding all my x components, all my y components, and putting them together to get a final triangle that I can work with. Okay, it's going to get a little more complex as we go along, but in the end, that's what I want to get to, is one single triangle that contains my resultant. Displacement, average velocity, average acceleration, whatever it happens to be. Okay. Questions on that one? Did those ones. Okay. All right, I'm going to give you a 5-minute break and then we're going to move on to something else. Okay, this one will be the angle vectors that go all over the place. Okay, so 5 minutes and then we're going to pick up there. Okay, guys, I need everyone to copy this question down. Okay, this is going to be our first example of vector component addition. So vector component addition works like this. Any angled line has a horizontal component and a vertical component. That is, it goes over and up or over and down, okay, if it's angled. Everybody okay with that idea? Okay. So what we want to do is draw every part of a trip like it's a right angle triangle and then find out it's over and up or it's over and down, okay, or it's x and y components. Once we break down all of our vectors into their components, their x's and y's, we now have positive and negative values that we can put together to get a picture of the whole trip. Okay, so we'll use this one as our first example. So first I want to draw the tail to head vector diagram for this situation. So I'll start out with the bus travels 25 kilometers at 30 degrees south of east. So start, and I'm going to draw a reference line that is due east because that's the direction it's measured from. It's 30 degrees south of east. All right, so I'll draw a little angle arc. It gives me about 30 degrees, and then I will draw my vector. Okay, so this is going to be 25 kilometers at 30 degrees south of east. That is going to have an x component and a y component. Okay, so they work just like your xy plots that you would have done in math. Okay? X is the horizontal axis and y is the vertical axis. Okay. After that, okay, it says that the bus turns and travels 10 kilometers at 45 degrees north of east. So what's my reference direction? East. Yeah. Okay, it went north of east. So I'm going to draw a reference line that goes east, but I'm not going to make it very long because this vector is quite a bit shorter than the first one. I'm going to go 45 degrees north of that, so about to there. close. Okay, my scale's reasonable here. I wouldn't say it's perfect, but it's probably reasonable. Okay, 45 degrees. I don't need that. That triangle also has an x and a y component. Okay. Now, does that line get back up to where I started? It does not. It falls short of it. Okay? That's where scale is important. If I make that too long, or I'm like, oh, it would sure be nice if this just went up to where I started, it doesn't ever works that way. You're not that lucky. Okay? So I'm going to get this really, really small overall triangle that looks like this. Okay, this will be my overall displacement. It has an x component and a y component, and it also has a very small angle in it. Okay. Does that purple line represent the overall trip? Right? It's drawn from start to finish, so that line does represent my overall displacement for that trip. Okay. So here's what I want you to see before we start getting into any of the math. If I take blue x, that is how far east I went during the 25-kilometer vector, and I add it to red x, how far east I went during the 10-kilometer vector, does that add up to purple x? Pointer. Looks like it to me, right? I just took the line I drew for red x and stuck it on the end of the blue x. Looks to me like it adds up to purple x. Would you agree? This isn't any different than the camper who went to the lake question. Okay? If I add the easterly parts together, I'll get how far east I went. If I add the north and south parts together, I'll get how far north or south I went. Now in this one of them is south and one of them is north, but that's fine. I'll just make one of them negative. Okay? Everybody okay with that idea? Right? Because if I add blue y to red y, the difference between those two should be purple y. Okay? All right. How do I go about finding blue x and blue y? They're part of a triangle, and I know the hypotenuse of that triangle, and I know one of the angles in it. Can I find the other sides? Using? Yep, I'll want to use sine. I'll want to use, in general, starts with T, trigonometry. Yeah, if I use trigonometry, I can find those other sides, right? Like, the rule is, if you know two pieces of information about a triangle, you know enough to find out all of it, right? You know an angle and a side, or two sides, or two angles. Okay, you should be able to figure out anything else about that particular triangle. Okay, so in this case, I know the hypotenuse and an angle, so I can find the other sides. All right, x, blue x, is the adjacent side to this 25-kilometer vector. Okay, so if I want to find the adjacent side and I know the hypotenuse, what trig function am I going to use? I want to find the adjacent side and I know the hypotenuse. Cosine, yeah. Because earlier we said the cos of theta, whoops, sorry, that should be in blue. Okay, so the cos of theta equals the adjacent side over the hypotenuse. I know what theta is, and I know the hypotenuse. I'm looking for the adjacent side. What do I do with the hypotenuse? If I want to isolate adjacent. Multiply it over to the other side. It's just algebra, right? Right now I'm dividing by the hypotenuse, so I'll move hypotenuse over. Now I'm solving for the adjacent side. Okay, so the adjacent side, which is blue x, is going to be 25 kilometers times the cos of 30 degrees. Okay, so it's going to be 21.65 kilometers. East. Okay, now, I'm keeping all those decimals in my calculator, okay? I'm not getting rid of them. I just didn't write them all on the board. Okay, but I'm going to keep them all. All right, what trig function will I use to get blue y? Since it's the opposite side. Yeah, at this point, I can use any trig function I want. I know more sides, right? Okay, but in this case, I would say my best bet is probably to use sine, because I was given the hypotenuse, and I'm looking for the adjacent side. Rather than use a number I calculated, I used the one the question gave me. Okay? So, the sine of theta equals the opposite side, which is y, over the hypotenuse. Okay? In other words, y over 25. Okay, so if I want to solve for y, I'll move it over, okay, and I'll have 25 times the sine of 30 equals the opposite side, which will be 12.5 kilometers south. Okay? Yeah, I just did trig in my head. Sine of 30 is 0.5. It's cheating. I use 30 degrees all the time, so I look cool. It's impossible. So. Okay, so now I know this side here is 12.5 kilometers. And this side here is 21.65 kilometers. Okay, can I do the same thing with the red triangle? In fact, with the red triangle, it's going to be even easier because the angle's 45 degrees. When the angle's 45 degrees, the two sides are? They're equal. Yeah, a 45-degree angle directly cuts that in half, right? So the two sides have to be equal on that one. So I only have to do one trig function on that. Okay, so for my red triangle then, if I want to find x, x is adjacent, right? So I'll simply go cos of 45 times 10. Okay, cos of 45 times the hypotenuse. Okay, 7.07. So that's both sides. Okay, so 7.07. Okay, so now I know all the sides of the first, or all the components of the blue triangle and the red triangle. So we just said a few minutes ago that if I took blue x and added it to red x, I would get purple x. So can I do that now that I know what their values are? Okay, so to get purple x, okay, I'm going to take 21.65 and I'm going to add that to 7.07. But I'm going to use all the decimals my calculator stored. Okay, so 28.722 kilometers. Okay, and then for y, I'm still going to add them together. I'm just going to make south negative, okay, because in one of them I go south and the other I go north. Okay, so for blue y was 12.5 kilometers south. Red y was 7.07 north. Okay, so we end up 5.43 kilometers south. Okay, so now I know the two sides of my displacement triangle. Can I use Pythagorean theorem now to get my displacement? I can. Okay, and then can I use trig to get the angle? I can. Okay, that's a vector component addition question. I break down 2 triangles, or 3 triangles, or 4 triangles, and I make one overall triangle. Okay, and then I do Pythagoras, and then I do trig, and then I'm done. Okay, it's always the same steps. Draw the picture, okay, break up the triangles, get your x's and y's, get your final triangle, do your trig, do your Pythagoras, and you're done. Okay, always, doesn't matter how many triangles there are, how many lines there are, it's always gonna be the same steps. Okay, now right now, if you're looking at me like you're a deer in the headlights, that's okay. Okay, this is probably the second trickiest thing in the whole course. Okay, but once you get the hang of it, it's really just a set of steps that you follow. You don't really have to think about it too much, you just have to follow the steps. Okay, and at first, you're only gonna get one of these questions done every 20 minutes or so. Okay, but then you'll get faster at it. And before you know it, you'll be doing one of these questions every 8 or 9 minutes. I'm not gonna say you're gonna like get 2 minutes, you're not, okay, but you'll get faster. Okay? They're involved, there's a lot of steps. I'm not gonna blow sunshine, you know. It's gonna be time consuming.
Can you really give us a picture? Like, give us the
I never give you the picture. I always give you the word question, and you have to draw the picture, because drawing the vector diagram is the trickiest part. Okay, the rest of it's just math. All right, so let's finish this one up, because we're not quite done yet. Nice.
Is this question?
Tyler, I keep calling you Tyson, sorry.
Based on like the other questions, how complex is this? Is this like the highest we'll go, or is this just intermittent?
Unless I was to give you one that had 3 or 4 vectors in it, this would be as tricky as they would get. It's not really trickier to have 3 or 4, it's just more work. It's the same thing 4 times instead of 2 times. Okay, but yes, it's definitely trickier than the campsite question, right? I mean, it's the same fundamentals, but yeah. All right, so now I want to look at how do I get purple D, or my overall displacement. I take the 2 sides, 7.07 squared, sorry, not 7, 5.43 squared. 5.43 squared plus 28.722 squared. And that'll give me my overall displacement. I don't want that to be negative, but it is in there. That won't matter because I'm going to square it anyway. Okay, so we're getting that the, nope. That's not right. Okay, so there we go. So we got 29.23 kilometers is my overall displacement. Okay, the magnitude of it anyway. Okay, so that's how long this, okay, that's how long this line is right here. Okay, and then I want to find, okay, what my angle is. Since I'm looking for this angle here, okay, can I use any trig function I want now that I know all 3 sides? So use your favorite. My favorite is 10. I like 10, I don't know why, just that's my favorite. But you can use whatever one you want at this point because you know all 3 sides of the triangle. Okay, so I'm going to go inverse tan of the opposite side. For my angle there, the opposite side is the 5.43. Divided by the adjacent side, the 28.722. And that'll give me my vector. But I don't want the negative. Okay, so I'm getting 10.7 degrees, which kind of fits with my diagram. It was a pretty small angle. 10.7 degrees south of east. Okay. Could I have the complementary angle there? Could I also have 79.3 degrees east of south? That would be fine too. Okay, is that a lot? It's a lot. It's why we spend quite a while on it. And so if you're looking at it today and going, I quit, don't quit. Okay? We're going to spend lots of time on this. And it's just a matter of repetition. The more of these you do, the better at them you're going to get. Okay? You're going to have to do some practice, but we got time for it. Okay? All right. Tomorrow, you will have a quiz. And I have to look. It's not going to be on this, okay? That would hardly be fair, okay? But I might give you like, a collinear one and an acceleration question, or just two acceleration questions. I haven't decided yet, okay? But I will post it right after school as always.
Look for Christmas, it's going to be on the quiz.
No, that's what I just said, not tomorrow.
No, I know not tomorrow.
Oh, yeah, absolutely. But there'd only be one, because they take two lessons, yeah.